Hello and welcome to today's seminar in the Smart Safety Connection series. My name is Joy Mann and I'm the Senior Administrative Coordinator at Safety 21 University Transportation Center. The Smart Safety Connection series is sponsored by the Safety 21 University Transportation Center as an opportunity for faculty to showcase their current transportation projects. It is also an opportunity for students, fellow faculty, deployment partners, and the broader community to engage and network with researchers, highlight opportunities for involvement, and foster future interdisciplinary collaboration. Please note the session is being recorded and all participants' microphones are muted. To ask a question, please send a message through the chat box. You do not need to wait until the end of the presentation to send your questions. Now I would like to introduce today's speaker. Dr. Zhuping Sheng is a professor in the Department of Civil and Environmental Engineering at Morgan State University, Maryland. He is a registered professional engineer, certified professional hydrologist, and fellow of the American Society of Civil Engineers. He has 40 years of research and practice experience in geohazard assessment and mitigation and water resources engineering. Please help me welcome Professor Sheng as he tells us about his University Transportation Center project, Improve Highway Safety by Reducing the Risks of Landslides with Smart Warning Systems.
Good afternoon, everyone. Can you see my slides?
Yes.
Yes.
One slides, right? All right. Thank you, Joe, for organizing. It's always tedious. Thank you for your support. And also, I'd like to take this opportunity to thank Roger and Karen for leadership for this UTC Safety 21 program. Today, I'm going to share with you some of the recent work my colleagues and myself have been done for improving highway safety by reducing the risks of landslides with a smart warning system. My team members, including Dr. Walabi and Dr. Yi Liu in our university. And most important here, we have partners, Dr. Cheng at the CMU. Also, I'd like to acknowledge Maryland Department of Transportation and State Highway Administration for their support. It complements our work as part of the UTC program. So I'm going to give you a brief introduction about landslides, what the relationship in terms of to the transportation system and what the impacts on the transportation safety and some of the method we are exploring, and certainly we cover UTC project outcomes and the collaborations, seeking more collaborations with other consortium members and other universities. First, landslides occurs everywhere. These slides occur just near the East Pittsburgh. On the left side, you can see in 2018, it damages road and the properties along the way. And on the right side, it is most recent landslides in Alaska kills people. So it really takes people's life when landslides occurs. And certainly you can see on the right side, the landslides also damage the road. Now on the left side, it's one of the slides that covers the highway. Certainly almost half of the mountains falling into the highways. Certainly it impacts traffic. Also, potentially cause impacts on the people pass through if they are driving through. On the right side shows the landslides occurred last year. Now here you see the atmospheric river means precipitations, stormwater, trigger landslides. So most slides have been triggered by precipitations, stormwater, and certainly some of the area might be erosion along the streams and so on. So precipitation is one of the major triggering factors. That's our study we focus on. We already talked about potential impacts on transportation system, loss of lives. It has economic impacts, billions, annually. What kind of asset we are dealing with in terms of highways, roadways? Certainly, when on the top you can see roadway, it cut the slope, then to build a roadway. Now, are these natural slope stable? Certainly, you stabilize this part, try to prevent potential failure. Are they going to slide down, or even this part will fail? And certainly, you have embankment to build up along the slope and to support highway or roadways. Are they stable? Are they going to have potential for failure? And also, you have ground improvement to support roadways. Whether these road foundations might pose threat to the road safety and the passengers' lives. What type of slopes failure? We have different types of slope failures. You can see rotational. When you drive along the way, you see something slide, shaped. That's a rotational. And some of them may be just sliding along weakness plan here. And certainly you have block slide, one block slide down, the next continues. Rock falls, when you drive along the way, you always see the signs, watch for rock falls, right? And for rock slopes, it can also have topper failures, debris flows, along the soft soils and debris range usually for sedimentary materials, earth flows. Soil can also creep. With the time, the soil can deform even on the same stress condition. So it can cause failures of the slope. And certainly lateral spread, when the condition allows, then rocks or soil can move laterally. So our goal is to reducing the risk. So this project is a multiple-year project. We want to ensure the safety of infrastructure system by preventing geohazard, specifically slope failure, landslides, and minimize the impacts of a geohazard with smart detection and the warning systems. This project addresses US DOT Research, Development, and Technology Strategic Plan goals is to promote transportation system, especially the physical infrastructure system and roadway designs, to address critical physical vulnerabilities. Our project objectives include assess the risks of landslides by looking into soil rock types, as I showed earlier, how the slides failure, certainly weather conditions, mechanical properties of slope materials, and other existing structures may also have impacts on the potential failure. Here we are using Maryland as a case study, using machine learning approaches. Certainly, we are open to other states. We are interested to partner with the research university, or state agencies. The second is to identify and map the high-risk areas based on the controlling factor geometry, mechanical properties of soil and the rock, and the triggering factors, including gravitational hydrologic forces, and use available survey data, remote sensing, and INSA LiDAR data. Then third objective is to design test protocols for real-time monitoring at selected sites in consultation with Maryland DOT staff. The fourth one is eventually we're going to develop or recommend strategies for reducing the risks of landslides with real-time monitoring for the high-risk area, improve the safety of transportation infrastructure. Both methods and strategies developed here can be transferable to other states or regions with similar geologic conditions and engineered configurations. What smart system here? Now it is integrated. You can see multiple components here. Now, I'm not going to read through each components here. Currently, Maryland DOT has precipitation sensitivity system built up. What we are doing is we want to use their existing data information and build a warning system based on that. Today, I'm going to cover landslide inventory we have done and precipitation data we're using for forecasting and prediction with machine learning tools, and the protocol for notification or alert system. The method we are exploring is to integrate geomechanic analysis, basically look at how the slope failure occurs, what are controlling factors or parameters for slope failure. Then use machine learning method to help us to use the capacity to evaluate or assess risks at different locations. Not all the locations has landslides. So we use the existing landslides to train the model to identify what factors controls. Certainly precipitation is one of the major factors we're going to use to detect or to predict that landslides at the different locations, different configurations. Now this figure shows we are using GIS platform to look at these maps, raster data, do qualitative analysis and quantitative analysis. Example, geomechanical model analysis. Then you eventually produce maps. And now next component is we fit this information into the warning system. That's what I'm going to cover in the next few slides. Then eventually notify the transportation administration to take actions in terms of prevention and also assure the safety of the transportation system. Now, geomechanical models here. Now, we have seen this in the field. When you drive along, you may see some of the failures. So you can see the failure, not necessarily always a straight line, right? So what we can do is simplify this to a slab sliding along the plane. Then it allows us to do analytical analysis. Otherwise, that's a circular failure. We have numerical method, certainly need a more effort in terms of simulation of the failure. So this one provides one of the base for analysis of slope failure. Now here you can look at the water table here, and basically assuming water flow through the slope, and at certain depths it triggers the failure of the slide. Not all the water coming to the slides cause failure. If it's a lower, doesn't necessarily trigger the failure. So how do we determine? We use safety factors, look at the soil properties, soil cohesion and the unit weight, and then determine the depths of the water you're looking into. Then phi is the fractional angles of the soil, and the beta is the slope angle. Now here, remember we look into the water within the slope can cause failure. So then we look into the critical head of water, how deep of the water in the slope could potentially trigger the failure. We use the safety factor equal 1, then determine the critical head of the water or depths of the water. From there, you can assess what potential precipitation may trigger the failure. So here F is precipitation sensitivity, depend on the critical head of the water within the slope. Then the first is the porosity of the soil, and second one is field capacity. It means in the field, soil may contain some of the moisture before the rainfall. So it means the soil's pore space has been filled with water. Only remaining portion will be filled by the precipitation. So this, as I said earlier, this project is partially supported by SHA or initiated by the Maryland DOT, think UTC grant to provide additional support so we can expand the scope of work. So this project is looking to the highway slopes or geotechnical asset. The state highway managers, basically roadways, the slopes, and one of the major factor is the precipitation. What potential impacts on the slope stability of the precipitation. So that's why this project called incorporating precipitation data into geotechnical asset management. So we have done some site visits, so that's why we know what kind of failure is. And this slope is along the Interstate Highway 68 on the mountain. You can see here, it's already protected, stabilized. But look at this part, it's an original failure. And you can, from this map on the top, you can see the multiple failures occurred in 2018, 2019. So first failure is 2018 September, then November, then January and February. So whole slopes has multiple failures occur. Eventually, block the roadway here. So, and you can see some of the was excavated to remove this debris. And that's from the other side to look at the stabilization project. But we noticed, even though with all this, project to stabilize the slope, we still see some failures continues because original field is more focused on the side and then bottom of the slope, but we still see the continuous failure. So one of the things we noticed, some of the slope may recur, or part of the slope might experience additional landslide. That's one of the lesson we learned, and it's also become a guideline for us. Certain area slopes can recur, so that's why provide us the lessons to prevent future failures. We have done some inventory assessment. So you can see the landslides across different counties distributed different ways. Certainly, it's related to the Earth's materials and certainly the conditions. But majority you can see in the middle. And other two slides show different counties, and also it occurred at different times. All right, so that's why you can see here, Prince George County and Baltimore County, Anne Arundel and Montgomery counties have majority landslides, historic landslides. Now, certainly it gave us the base to evaluate risks in this area. So these case studies will be used to train the machine learning model and also for geomechanical model analysis. Now, the other interesting feature you can see here, landslides occurs different years, but 2011 and 2018 has more landslides. Are they more related to precipitations? We are looking into it. Or are there other factors play the roles? Certainly, this shows different patterns in terms of temporal distribution, and this one shows the spatial distribution, so we can target certain area where the most landslide occurred. We just started to use images to potentially detect or identify existing failures or even detect future failures. So we are using LiDAR data. These two LiDAR data from 2 different years. What we do is we compare them to look at differential movement vertically. So if there's a sharp movement or displacement, then we can assure there's potential failures or historic failures. So we can check and use it for future predictions or detections. So this one shows the differences. And now we haven't go to the site yet. We are planning to. So we verify site, field ground truthing the site, what they really meant. The red means the height, the differential differences between 2 years. So if everything goes down together, then you don't necessarily see the failure. If they see one side is moving up, the other side is moving down, then you know there's a potential failure. That's what we try to detect. We are developing collaborations with the CMU on this in image processing and interpretation with Dr. Briggs. They have done, great job in previous work. So we're going to team with them to potentially transfer some of the technology they have and use it in our project. Now, Dr. Sheng and Dr. Bingui have done evaluations in terms of precipitations. Remember, one of the major factor is the precipitations. Can we use precipitation data to estimate what's the threshold of failures, then use these as an indicator to evaluate the risk of failure for the slope. And certainly then we can set up warning system or send alert or notification to the state highway staff so they can take actions through different venues, email or text message and so on. So they already developed a dashboard protocol. So I'm going to show you the next few slides. They evaluate multiple sources of data. One of the challenges, where do you get the data? Are these data reliable? Are they free or lower cost? Certainly, for state agencies or any organizations, cost is one of the factors for their long-term use, because that's not only for 1 year study, it's for future applications. So Dr. Sheng and Dr. Bingui has evaluated multiple sources of data, and eventually we recommend Open Metro data is one of the top options. They have done some comparison between different data set. Eventually, data set, Open Metro data set still stands out. So, and also develop raster plots, for different time frames, and we take Allegheny County as example. Basically, that's what the State Highway selected. So we use this as a case study for initial settings, and we use NOAA grid size 2.5 kilometers. So within this county, we have a total 255 cells. This one shows historic hourly precipitation data from Open Metro data. That's hourly. You see the variations of the precipitation data across the county. The tested dashboard, again, we're using the Allegheny County. State Highway has identified 407 slopes along the highways or roadways, and we're using Open Metro data as example. So then, detect what's the high risk area. Now, with precipitation data, you can trigger the notification or warning once it exceeds threshold. Now, State Highway want to look at different time steps, from several hours, 1 day, 3 days, 7 days, 2 weeks, 30 days. So the model we're developing is going to provide this kind of data set that State Highway is interested. And dashboard send notification. They have tested on the Jupyter notebook. we randomly select the 20 slopes within the Allegheny County. Use 30-day historic data to test it. 10-day hourly forecast data to for each slope and choice, and monitor the precipitation warning based on the high-risk area or moderate risk area. This one, it also pops up with information where they're located if it detects potential failure or need attention. So the state harbor will determine what measures need to take once we detect these potential failures. Next step, we are building landslides susceptible map model for Maryland. Basically, we are using the protocol Dr. Chu and Sheng for Zhuping, I think. But we are adding more refined precipitation data in terms of temporal scale, and also has more machine learning approaches incorporated in the assessment. Second part is to integrate geomechanical model analysis with the landslides risk assessment. State Highway already provide geotechnical asset over 10,000 slopes available. So we are going to integrate some of the geomechanical model assessment based on the soil type they already have, based on the USDA soil type, and also there's another group looking into geotechnical perspective. So we are going to hopefully integrate it. There is for landslides risk assessment. Again, we will continue image processing interpretation for detection of landslides. UTC project is unique. We're always looking to outcomes, workforce development. Certainly this program will support graduate students at this school. We have a new PhD program in sustainable resilient infrastructure engineering program. So we will have students enrolled in this program work on our project. We are also teamed with National Center of Equitable Artificial Intelligence and Machine Learning System Center to support summer internship. They provide support. We try to partner with them with our support. So it basically expand our effort to achieve our goal. As I said earlier, technologies, method, strategies can be transferable to other states, other regions. So as part of this project, we'll produce maps of landslide risks and make it accessible to SHA or UTC system. We provide training workshops for SHA staff and other professionals in transportation safety and disaster management. Certainly, we develop course materials, more workshops, and so on. Now, the last one is critical. The protocols we develop for monitoring of slope movement or failures and warning system can be transferable to other regions, other states. So we're looking forward to that. again, I want to emphasize the partnership between state agencies through this 4 projects you can see here. MSU and CMU partnership has a long history, and also state highway and UTC program demonstrate a great partnership here. We are looking forward to more collaborations with other universities within the consortium, certainly beyond the consortium, for partnerships, collaborations. In summary, landslides has a great impact on transportation safety. It also can cause people's life. Precipitation is one of the triggering factors we are focused on. Certainly, there are other factors, but this initial focus is related to precipitation. And we are developing integrated framework, including geomechanical modeling and AR machine learning approaches. Eventually, we want to have the early detection and the warning system for prevention of the slope failure. Certainly, it aligns with US DOT strategic plan to assure or promote transportation safety from physical perspective and to address critical physical vulnerabilities. Thank you for your attention. Any questions?
Hi, this is Chris Hendrickson at Carnegie Mellon. Can you hear me?
Yes.
Okay, very impressive. I really like how you're doing all the integration and partnering, and also integrating things like workforce development. So this is all to the good. I was curious about the LiDAR data that you were showing. I was wondering how that was collected, and you were showing differences between one year and another. And I was wondering whether the way it's collected, I assume by airplane or drones, would affect that sort of comparison.
That's great. Good question. Thank you. This image is provided by Maryland DOT. So we acquired this data. In fact, it's online. People can access this data. And we were expecting more LiDAR data. What you raised concerns really valid and valuable. Certainly how you assure the quality, especially when we use this data to detect, identify potential failures. I guess if in the future, state highway has better, more control on the data collections, certainly these factors should be considered. I don't know original protocol how this data was collected. Appreciate the question. We can look into it.
Thank you.
And sorry, the other thing is most recently they are expecting more LiDAR data available, but was delayed. Thank you.
Any other questions for Professor Sheng? That's it, Professor Sheng.
Well, thank you.
Thank you.
Okay.
And thank you for sharing your work. To all today's attendees, thank you for joining us. As I mentioned earlier, today's presentation will be posted on the Safety 21 What's Happening page of the website, along with a link to the video of the session. For
Okay.
students who are interested in engaging in transportation topics, the Transportation Club on campus is a great way to plug into transportation topics with fellow transportation enthusiasts. Our next Smart Safety Connection seminar will be held on Tuesday, March 29th, and will feature Professor Steve Smith, so please watch your emails for the invitation. And thank you for attending today's Smart Safety Connection seminar.
Thank you.
Thank you, Dr. Sheng.
Okay, bye.